compactness. Consider a topological space. Consider a topological space X. Then X is said to be compact if every open cover of X. So what is the meaning of open cover? So write X as union of some open set. Suppose X equal to union of Ui, where Ui are open. Then this is an open cover. If every such open cover has a finite subcover, then we'll call X is a compact topological set. Compact topological as X can be written as union of so compact means every open covering of the topological space has a finite subcover. It can be defined for any subspace also, because subspace admits a relative topology, and we can consider that topology to define if it is compact or not. That means for subspace, alternatively, we can say so a subset A is compact if every open cover has a finite subcover. This is the definition of compactness. Open cover means, suppose A can be written as union of A is contained in union of Ui. I belongs to I. Then it has a finite subcover. That means some of those UI1 up to some UIN, like this. So this is the definition of compactness. Let us see some property of this compactness. So first one is, if we consider X as a house dot space, then A is compact. A is a subspace of X. This is compact, implies A is closed. Okay. So this means every compact subspace of a topological space, house dot space, is a closed subset. Okay. This observe. This is an easy observation. You can do this. Another thing is, a closed subspace let me write the properties one by one. of a compact space is compact. This is also easy to see. Suppose this is a topological space X and this A is compact. Sorry, A is closed. Suppose X is compact and A is a closed subspace. This is closed. Then what can we do? Simply we need to prove that A is compact. Means A has a finite subcover. So consider open cover of A. So this kind of open cover if we consider, then it is also clear that x minus a, if we take x minus a together with those previous cover, then x minus a is also open set because a is closed. Already we have assumed a is closed. Then this complement of this thing is union of those previous open covers. So this forms a open cover of X, and therefore it has a finite subcovering because X is compact. It is already assumed. Then take that finite subcovering. So it is already finite. So there, the only finite appears because of this open cover. So take that finite covering. Clearly, that will cover the space A. Right. That's why A is um, every compact, every closed subset of. Those are some important properties. Another thing is that compactness preserved under a continuous map. So let f from x to y, this is continuous. Then image of a compact set is compact. F applied on a compact subspace is compact. Why this is true? Again, this is also easy to see. So take a subcovering. Suppose suppose A is compact, then its image. So suppose this is the image f of A. We have assumed if A is compact. Then consider an arbitrary covering. We need to prove that this arbitrary covering has a finite subcovering. So how can we prove that? So take the pre-image under the map F, then F inverse of those open sets. So those are UI, those are open set. Now this A is F inverse of those UI covers A, and we have already assumed that A is compact. So it has finite subcovering. A has finite subcovering, and use this subcovering. So suppose F inverse E1 up to UM, those are the finite. E1 up to UM, that will be subcover of 1. This property is also equal to C. Now another important fact. This is not very straightforward. Some tube lemma can be used. The product of compact subspaces is compact. Okay? Product of compact spaces, compact spaces is compact. Consider x1 up to xn. Those are compact. This will imply x1 cross x2 cross xn. This is also compact subspace. Okay. So those are some important facts. Another thing, another definition of compactness in terms of finite intersection property. So we can define compactness. Up to this, compactness is completely defined in terms of open set. Now we are trying to define compactness in terms of closed set. finite intersection property. Suppose consider a collection A equal to AI, or consider the collection C equal to C1 Ci, where I is the index set. So this is a C is a sub C contains subset of X. Okay, subset consisting subsets, some subsets of X of a topological space X. Then C is said to be satisfy finite intersection property if, or we may call C has finite intersection property if for any, choose any finite collection C1 up to Cm, then their intersection is non-empty. Cin, where n equal to some 1 up to n, in non-empty. For all this is true for any for any finite collection. So choose some finite collection from this set. For example, Ci1 up to Cim, I have chosen that collection. So their intersection is non-empty. Then this is called finite intersection, because intersection has uh, finite intersection is non-empty. Now we can define compactness in terms of finite intersection property. This is actually contrapositive statement, very straightforward. Proof is very straightforward. X is compact if and only if this is the following is true. That is, every collection of closed sets in X, every collection of closed set in X having finite intersection property, this is called finite intersection property. The intersection, now we can consider the whole intersection, right? Intersection of all C, where C belongs to this collection. So if it satisfies finite intersection property, then the whole intersection is non-empty. If this is true for collection of such collection of closed sets having finite intersection property, then this is the space will be actually a compact subspace. And moreover, C is non-empty. We have chosen only non-empty set. Otherwise, intersection will be automatically empty. We need to discard those empty choices. Okay, if X is compact, if this satisfies the following property, and if if the space satisfies this kind of property for any collection of closed sets which satisfies finite intersection property, imply this. If the space satisfies this kind of property, then X will be compact. This is completely contra-positive statement of contra-positive statement of concepts of Okay, sorry about this. There is some issue in Wi-Fi. Okay, so compactness can be alternatively defined by this finite intersection property. Those two definitions are exactly same, just a contrapositive statement. Now let us see some properties when we deal with metric space. So if X is a metric space, and A is a subset of X, then A is compact. This implies A is closed. Okay. So compact, compactness will imply it is closed, and moreover, so this is true for Hausdorff space. This is and metric space is in particular a Hausdorff space. Therefore, A will be compact. A is closed. Moreover, if we consider a metric space, then there is a condition of boundedness, right? There is a notion because in metric space we can say something is bounded means it contains some open finite radius open ball, right? Something is bounded, a set is bounded. Suppose this is a set A is bounded if A containing B0 comma some radius finite radius r, right? So there is a notion of boundedness. Then this is closed. Moreover, this is also bounded. Again, this is very easy to see. Just use this kind of open cover. This open cover will always, by compactness, this is open cover of R, hence it will be also open cover for R2. Therefore, this will be also open cover of any kind of subset. And compactness ensures it will be covered by some finite number of such concentric open nodes. Okay, so therefore it is uh, bounded. Now, in particular, so the converse may not be true. There are spaces if we consider infinite dimensional metric space, infinite dimensional, or uh, if we consider this kind of thing. Uh, so, for infinite dimensional metric space, this may not be true. Okay, there can be compact set which is not closed. This occurs in Hilbert spaces. So it is a metric space with a particular norm. For example, that norm can be, you can consider the norm as 1 by 2 to the power n, sum of 1 by 2 to the power n, modulo. That is, the usual norm is that square root of xi square minus yi square, sum of these, right? But for that, we can consider the norm as there are infinite dimension, so this is not enough. We need to divide it by some 1 by 2 to the power n or something like this, which depends on the component I. Something like this, 1 by 2 to the power I. I cannot recall the example, but in this case, some of this. So in this case, if we define the distance in this way, then it is not actually a compact. Means their closed unit ball is not compact. So converse may not be true. Okay, but converse is true if we consider Rn. finite dimensional case. In Euclidean space, if X is Rn with usual topology, that is Euclidean space, then a subset A is compact if and only if A is closed and bound. This is very interesting property. It always not the case, but for R, for Rn, closed and boundedness is enough to say it is compact. Actually, the proof of this can be obtained from that R satisfies every closed interval of R is compact. Okay. From there, this can be proved very easily because in this case, closed and bounded, that means boundedness imply it will be subset of some intervals like this minus k comma k to the power n. So every ball can be thought of as subset of this kind of square. Okay, so instead of square it will be n cube. Now finite product of compact set is compact, so this ball is compact, and the set A is bounded, so A lies in this kind of subset, therefore A lies in this kind of compact set, and A is a closed subset of a compact set, hence A becomes compact. This is how we can prove this fact. Okay. Now another interesting theorem is extreme value theorem. So consider a continuous function, continuous map f from x to y, and assume x is compact. Those are hypotheses. Then the image fx has minima and maxima. That is, extreme value is always at it. Okay, minimum and maximum. So there exists, explicitly stating, there exists some fc and ft such that all fx contained in this. This is true for all x. There exists fc, there exists c comma d such that fc less equal to fx less equal to ft. So image set attains its extreme values. So why to attain this kind of inequality? Why should we order topological space? In particular, let us consider R only. And this is so those are some properties. Another thing is that again, continuous map may not be uniformly continuous. What is uniformly continuous? Uniformly continuous, that restriction is not a local restriction. So dxy less than some delta, so f is uniformly continuous. This is the definition if the following is true. That is, let epsilon greater than 0. So we consider uniformly continuous in metric space. X is a topological space. XY, F is a map from one metric space to another metric space. dfx, dfy less than epsilon for epsilon greater than 0, there exists delta greater than 0 such that this is less than x. Whenever the distance between x comma y less than delta, it will imply d of fx comma fy less than epsilon. Okay, so this says this is not restricted to a particular point. So here this delta does not depend on the choice of. So we are not taking neighborhood of fixed x, right? So here x and y can be any 2 points. Okay, x is not a fixed point for which we are taking neighborhood. That is y from. We are not picking uh, the point y from a from it's from neighborhood of fixed x. So here x and y can vary. So this is the topological space. X and y can vary over this topological space. Any 2 point whose distance is less than delta. Okay. So x and y those are not fixed. For continuous map, in the definition of continuous map, this first x is fixed. So we choose a point and we vary another point in the neighborhood of x. So this is the definition. So uniform because we are varying x and y both uniformly, such that their distance is less than delta. So the interesting thing, so something is continuous, a map is continuous may not imply that is uniformly continuous. But if the domain is compact, if the domain is compact, so if the domain is compact, then continuous and uniformly continuous both are same. Then f is compact, f is continuous, if and only if f is uniformly continuous. So those are some important facts. Now let us solve a few problems. So in first problem, we need to see which of the following are compact. Compact subset of the topological space are real number with a given topology. Those are some choices. So first, so we need to see if 0 close 01 is compact or not. So for first problem, if we choose usual topology means Euclidean. We know for usual topology, closed and bounded, those two conditions are enough to say it is compact. So closed 01 is bounded and closed. This is closed interval, hence it is closed. So this is closed in R with usual topology. So this theorem is only true for R with usual, means Rn with usual topology. Therefore, this is compact. 01 is compact. CPT, I am denoting CPT for compactness, compact shorthand. Now what about B? Even cofinite topology, then can we say something like this? If we consider cofinite topology, then we can, in this case also we can say this is uh, compact or not. So let us consider any covering of the topological space 0, 1. So close 0, 1 containing some arbitrary union of, or maybe U alpha. Alpha belongs to some set A. Okay, U alpha equal to open set. Okay, close 0, 1 containing this. So to prove compactness, we need to prove that close 0, 1 that can be covered in a such finite collection. Okay. So note that we are considering cofinite topology. For B, we are considering cofinite topology. Therefore, choose any U alpha. Suppose choose U alpha 1, any U alpha. So its complement is finite, right? Note that all U alpha cannot be empty, because if we consider all U alpha, those are empty sets, then their union cannot contain interval. Interval has infinitely many points, which cannot be contained in empty set. So choose a non-empty of U alpha non-empty set. Then, by definition of cofinite topology, U alpha 1 complement is finite set. Okay, maybe which equal to this. Consider this x1, x2 up to some xn. Okay. So this is the finite real number which is there in the complement. Now, there are two cases. One case is close 0, 1. If close 0, 1 containing this U alpha 1, then we are done. Then we are done. This is the finite subcovering. Now, if not, then it may happen. So close 0, 1 containing union. So it may happen uh, close 0, 1 close 0, 1 minus U alpha 1. So this will be a subset of this x1 up to xn, right? Because U alpha 1 is nothing but, from here it is clear that U alpha 1 is nothing but R minus this x1 up to xn. So if we remove U alpha 1 from this interval, then this must be a subset of x1 up to xn, right? This is true. Okay. It may contain all of those points or any subset of this. So take then, suppose if xi belongs to 0, 1, then by open covering property xi belongs to some alpha I, then xi belongs to some u alpha I, right? U alpha I, let me denote it by u alpha j. Okay, so xi belongs to 0 1, then xi belongs to some u alpha j. But this will imply so this will imply u alpha 1 union u alpha j. This contains that xi points to, right? So consider all such xi's. Okay, xi belongs to 0 1, xi belongs to u alpha. So choose those xi only. So then from this collection there are only finitely many cases, and all those xi belongs to some u alpha j. Then this u alpha 1 together with the worst case is take all those things belongs to the complement. In this case, choose all other things u alpha j's. Okay. Let me consider the only finite choices. Some one day, each one up to xn, a subset of this. Let me denote it by y1 up to yn. So for each y1, for each yi, choose choose a choose an open set. Then those open set j so this is now the finite subharmonic u alpha 1 and u alpha ji. Okay, let me denote it by some notation. U Let me denote it by u0. First one as u0. Let me simplify the notation. First one is u1 and all those things maybe u0, and all those things are yi belongs to u1, and u0 u1 up to un, the finite subgroup. So this is the proof that not only if, so the proof does not depend on the closed interval 0 1, right? So the same proof can be applied for any subset. So any subset of a cofinite topology is compact. Now what about co-countable topology? So is closed 0 comma 1, is it compact with respect to cofinite topology? So let us see. So consider the open covariant. Denote ui or un equal to closed 0 1 minus 1 by. Is it enough? No. The opposite way. 1 by n up to infinity. For example, u1 contains everything but Even means 1 by n comma 1 by n plus 1. So this is we are considering co-countable topology. So this is countable set, hence its complement is open. So this is open in close 0 1 with respect to the countable topology. Okay, and moreover, this close 0 1, this can be written as union of this un, right? N equal to 1 to infinity. First one contains complement of the set 1 by n, that is 1 half 1/3 etc. Second one is the complement of this set etc. So the intersection, if we take union, then it will be close 0 1 because we because take any 1 by n or any 1 by n. So it is already up to 1 by m um. So 1 by m does not belongs to um, but after n 1 by m belongs to um plus 1. So whatever 1 by m you choose, it always belongs to some um plus 1. Therefore the union becomes closed 0 1. All those points are all those points, whatever points is not there, it will belongs to some um. For example, this 1 by m belongs to um plus 1. Therefore this is the explanation why this is good. Now note that this is compact. Why? This is not compact. Why? Because if we choose finite subcovering, if we take a finite subcovering, suppose u n1 up to u nk, this is a subcovering, and also assume so un1 means it start from this 1 by n1 plus, so it does not contains from this 1 by n1, right? So the is their union cannot contain whole 0 1, because what is happening here, for example, if we consider u1, let us see some example. u1 does not contains the point 1 half etc. u2 does not contains the point half onwards 1/3. So if we take union of those two things, then it is clear, then it cannot contains this 1, right? Sorry, it contains 1, but their union cannot contains the points half and after all the points half 1/3, their union cannot contain this. So from here, assume the minimum of n1 up to nk, this is some nl. Okay, so if we assume, then union of unl, sorry, union of this unk, ni, I is from 1 to k, does not. So this union will be. It is clear that the union sorry, not minimum. We want to consider maximum because the U1 union U2 will be U, right? The higher you choose, their union becomes U1 union U2. This becomes the higher one because there is a chain like this. So the whole union becomes UNL, and this therefore it is clear. Therefore, 1 by NL does not belong to the union. I equal to 1. Hence, this copper this copper n belongs to n has no finite subcover. We are getting a contradiction. Right? So we have chosen a subcover n1 up to unk. Then choose the maximum of n1 up to nk, which is nl. Then from this observation, it is clear u1 lowered the index. It is already contained in the for example, U1 is already contained in U2. So their union will be the highest, that is maximum of this. So that's why union of UNI, this becomes the maximum index, UN. And by definition, UNL cannot contain 1 by n. For example, U1 cannot contain 1. U2 cannot contain half, like this. So, so that cannot be, the union cannot be whole zero, close zero. That's why it has no finite subcode. Now, what about lower limit topology? So, up to this, we have proved this is compact in usual topology. In cofinite topology, every subspace is a compact subspace. In co-countable topology, this closed zero one is not compact. Now, lower limit topology, again, that will be not compact. Why? For lower limit topology, note that closed union of this kind of open set, 1 minus 1 by n. So we can approach towards 1 from this left, right? Take half in 1/3, right? Half then 1 minus 1/3, which is 2/3, 1 minus 3/4, like this. So we are approaching towards this 1. But this union, if we take this union, this n equal to 1 to infinity, this is not closed zero. So those are open set, but open in lower limit topology because left side is closed, right side is open. So we also need to include the point 0. Take this union and take the union of singleton 1 because 1 is not included in the union. And we also note that 1 is open in this lower limit topology because 1 can be written as closed 1 comma sum 2 open 2 and take intersection with 0 1. So 1 is open relative to this closed 0 1. As in the subspace topology, this 1 is open. Okay, of the lower limit. So this is actually this thing will be a open covering, but the problem is it has no finite subcovering. You can see that if we choose some finite choice 1 up to k, then there is a huge gap, right? 1 by k, there will be huge gap because this was approaching towards 1. So up to 1 k, this is 1 by k up to 1. That whole interval is not there. This is the issue. So if we choose n equal to 1 up to k, then again those are actually chain. One will be contained in another. So the union will be 1 by k itself. So this 1 by k up to 1, this will not be covered by this subgroup. So that is the problem. So from here we can say that it has no finite subcover. This is again false. This is not compact. Now question 2. Here f is a continuous map and given x is a compact space, y is a Hausdorff space. Then which of the following are correct? So first two option says f is a closed map. Take a closed set. Let a equal to a closed set. Okay. Then f of a. Now we have already assumed x is compact. Closed subset of x. Of x. You have assumed that f is compact. F is a is x is compact, and we know every closed subset of a compact space is compact. This implies a is compact, right? Now apply f. F is continuous, therefore the image under a continuous map is again compact. So Fa is compact. Now we have assumed Y is Hausdorff. So Fa is compact subspace of Hausdorff space. This is Hausdorff. So we know a compact subspace of a Hausdorff space is closed. Therefore Fa is closed. So this option is correct. F is closed map. We have assumed a subset. We have taken a closed subset, and its image become another. Now what about cosine map? We know continuous map. So in general it may not be cosine, right? Because we don't know if it is surjective or not. Okay. So this may not be true because it may not be surjective. For example, consider the inclusion. Close 0, 1, counter example. This is compact x equal to close 0, 1, and consider the inclusion in R. R is Hausdorff space. So this is not a cosine map. So when will it be a cosine map? Moreover, if f is surjective, that condition is given. Okay, so this is not true. If it is surjective map, then we can say this is a cosine. If is homeomorphism, if it is a bijection. So this is true. Why this is true? See, f is bijection, in particular f is surjective map, therefore it becomes a cosine map, right? And why? Because f of closed set is closed. So if we choose any closed set from the codomain, sorry, if we choose any closed set from the codomain, then their inverse image is open because f is continuous. Now conversely, if we choose a closed set from the domain, by this property, as we have proved in A, by this property, their image becomes closed, right? And this is one of the definition of cosine map. So in terms of open set, we can define in terms of closed. So C is also true. Now what about D? F is an open map. So this is false. Okay. Counter example. Take this one. That counter example is already produced actually. We have already seen in previous lectures quotient topology. So consider this topological space. This union with this. Okay. So this is actually a closed subspace -1 to 0, and we are considering this I closed interval closed. That is this union -1 0 1 plus -1. So this already. So consider this and take the quotient map by projection. So take the continuous function by projection. From here, define x equal to this. This is compact because closed and bounded subset of R. So define x to R by simply projection f of x comma y equal to x projection on x. So this is not open, though this satisfies the property. The x is compact by first term, but this is not open. So we can consider uh, this open. This open right? This dot is open, but the image here is not open. Yes, it is not open. Let u equal to close 0 comma 1 union open 0 comma closed 1. This is open in X as a relative topology. X with relative topology, subspace of R2, Euclidean space. But f of u, so we can see the image becomes closed 0. This is not open. Which of the following are correct? Are compact subspace of R2. First one is open unit. So if you consider open unit wall, this one, then the problem is this is actually bounded. Boundedness there is no issue, but this is not open unit wall cannot be closed. This is not closed. Not closed, therefore not compact. Is false. Now for B, it is already closed and it is unit wall, therefore bounded. Closed and bounded imply this is compact, so this is true. Now what about Q cross Q? Q cross Q is neither closed nor bounded. Okay, so Q cross Q is false. Even if we restrict Q cross Q intersection with this interval cross interval, that is, if we make it bounded, then this is also not because of the same issue. This means this is not a closed set. There are whatever neighborhood we choose, rational pair that contains lots of irrational pairs also. So C is not true. Now what about D? C is not true, not bounded and neither closed. X comma 1 by x. X non-zero. So this kind of thing, hyperbola. So again, the problem is this is a closed set. There is no issue. This is closed. Any graph is closed. Whatever point you choose, that is, whatever sequence you choose, their limit point is always there, or limit point of the set is already there. In this way, you can say this is a closed set. Otherwise, you can directly look that by direct definition that complement is open. Whatever neighborhood choose there exists open ball like this in the complement. So this is closed, but this is not bounded. Closed but unbounded. Because whatever neighborhood we choose, we cannot contains it cannot contains that point. It always excludes some points, right? Not even some, lots of infinitely many points. So whatever neighborhood, for example, bx, b0 comma some r, whatever neighborhood we choose, then we can always find an element like this, r plus 1 comma 1 by r plus 1. So this does not belong to this neighborhood. Okay. So this is unbounded. This is true or false. So we are considering a map from R to S1 defining by f of t equal to e to the power 2 pi it. So we are thinking S1 as a subspace of complex number. So e to the power 2 pi it means cos 2 pi t comma sin 2 pi t. This kind of pair if we think it as subspace of R. So in this case we need to see if the image is compact. Okay. So let us denote A equal to this set 0, 1, half, etc. So this is closed and bounded. Closed bounded. Boundedness is clear because it is bounded because of A containing this ball, unit ball. All those points are already there in the unit ball. Half, 1/3, etc. 1. 1 is not there. So now A is bounded. It is closed. Yes, it is closed because the limit point of the sequence 1/2, that is 1 by n, converges to 0, and 0 is already included in the set, so it is closed. Otherwise, you can see that complement is union arbitrary, means some countable union of open set which is open. So this way it is closed and bounded, but we know that f of compact set, so closed bounded means it is compact. So f of compact set is compact. Hence this is true. Therefore it is true. So in this problem, the collection A consists this set n, which is defined by this open interval 0, 1 by. So we are considering a collection of subset of real number. Now the question is the intersection non-empty? Yes, satisfies finite intersection property. So note that if we take finite intersection 0, 1 by n, suppose n equal to this n equal to this kind of thing, n1 up to n. If we choose this finite intersection, then again here you can see 0, 1 containing 0, half containing this 0, 1 third, like this. This is nested intervals. Therefore, this will be 0, the union will be one of the thing, right? The biggest interval from this largest interval. So this is 1 by some n, and take maximum, minimum of this choice n. So here we have chosen n1 up to nm. Let n0 denotes minimum of n0, n1 up to n. And it is clear their intersection is none. So this is 0, n0. So this is rough. So A satisfies finite intersection property. Now finite intersection property says so those are actually closed subset of a compact set. So it should satisfy the property if this is if this collection has finite intersection property, then their intersection should be empty, right? Now the problem is those choices are actually not closed. So in that property we need to choose closed subset. Recall the property, the alternative definition of compactness. In this case, we need to choose closed subset of that given set. Though this is a subspace of a, it satisfies finite intersection property, but the collection are not closed subset. So therefore, the empty may not be true. It is possible their intersection is empty. So in this case, this is the case actually. So if we take intersection of all those things, n belongs to n, then this intersection is actually empty. Because whatever point you choose, whatever xi you choose, xi will be less than some 1 by n, ni, right? And therefore, the intersection becomes empty. So, but 1 by ni, 0, 1 by ni is also already there. So, this is not possible. This is true because of Archimedean property, right? Therefore, the intersection is empty. Archimedean property says the intersection is empty. So, A is not. So, in that property, always remember that this subset should be chosen as closed subset. Otherwise, that is not equivalent. Okay, the closed subset compact does not imply arbitrary intersection is non-empty. Though it satisfies finite intersection property, but those collection does not contain closed subset. That is the issue here. Okay, so let us drop here. the next tutorial we see some problems from locally compactness and those kind of things, sequential compactness and one point compactibility. Thank you.